Alright guys, we are back talking about statistics again, specifically hypothesis testing, and more specifically, we're talking about population proportions using sample data to make a decision about a population proportion, to figure out if a population proportion has, in this instance, gone down. But you can use it to test if a population proportion has gone up, down, or just simply changed. Okay, so let's get right into it. In March 2016, Gallup found that only 13% of Americans approved of the job the United States Congress was doing. Okay, suppose that in April of 2016, so a month later, a random sample revealed that just 111 out of 1,000 Americans approved of the job the United States Congress was doing. At a 5% significance level, can we conclude that the true population approval rating of the United States Congress has decreased over the past month? Does this conclusion change or remain the same if we increase the level of significance to 1%? So, we're talking about approval ratings of Congress. Obviously, they're pretty low these days. Most everybody thinks they're not getting much accomplished. Well, they're not getting much accomplished. And so, we see that a month ago, 13% of Americans approved. Okay, so that is what the population proportion is known to be. Now, if we remember our symbols correctly, that is P. So P equals 13%. Now we need to write this in decimal form. So 0.13. Now we take a sample a month later and find that 111 out of 1,000 approve of Congress. Now remember, sample data, a sample proportion is P hat. So that's 111 out of 1,000. So in decimal form, of course, that's 0.111. So we have P hat, which is sample data, and then we have P, which that is population. Let's see if I can do that. Okay, there we go. Okay, so let's see here. What do we need to do first? Okay, you remember with confidence intervals and the last few chapters when we have dealt with proportions, sample proportions, and population proportions, before we could use the z-table, before we could even get started, we needed to check two things. We needed to make sure our sample size was large enough so that we could use the standard normal distribution, the z-table. And if you remember that, we needed to show that NP was greater than 5 and NQ was greater than 5. Okay? Well, let's check that here. N, of course, is 1,000. That's our sample size. So we need to check to make sure these two guys right here are true. Well, if P is 13, so 13% of 1,000, that's certainly greater than 5. Now Q, now remember what Q is. Q is 1 minus P. Okay, so let me write that up here. Q equals 1 minus P. So if P is 0.13, that would mean Q is equal to, let's see, 0.87, or 87%. Okay, of course, 87% of N, which is 1,000, that's certainly greater than 5. So both of those check out. So we're good. We can use the standard normal distribution, and that's what we want to do later on. So you always want to make sure to do that before you get started. Most of the exercises that I give you, that's going to be fine. Your homework and tests, but you always just want to double check. Okay, because there will be questions that say specifically, can we use the standard normal distribution with this particular exercise? So the question there is simply answering if NP and NQ are greater than 5. Okay, so let's see here. Now let's talk about hypothesis testing again. Now let's change here. Hypothesis testing, we've done several examples now. That's when we're going to use the sample data to see what's going on with a population parameter. Okay, so the population parameter here is P, which is 0.13. We have a sample statistic here, which is 0.111. We want to see, obviously, if you just look at the sample proportion is smaller than the population proportion. So we would suspect that there is something going on there. You know, it's not guaranteed, but we would suspect. But we can't, declare that the overall approval rate in Congress has decreased just by this 1,000 people. We need to crunch some numbers first and see. Because it's quite possible that we just picked, when we were making phone calls for this 1,000 sample size, that we happened to reach people that happened to be more disgruntled in the population. You know, that the people that wanted to talk to us, they were particularly, not happy that Congress hasn't been doing anything, and so they just happen to pick up the phone more often than people who are pleased with Congress. So there's all types of reasons that could be that that this sample had a lower approval rating than the population. Now we want to see if it's a trend or not, and that's where the hypothesis testing comes in. Okay, so what was step one? Okay, step one was always state your null hypothesis, H sub 0, and state your alternative. Sometimes written as H sub 1 or H sub A. I remember I told you the other day, I usually write like this because students tend to remember ho-ha. Yeah, the ho and the ha. Okay, that's the null hypothesis and the alternative hypothesis. Now, what is the null? The null is the status quo. That's what has been shown to be true in the past. What's shown to be true here is that P equals 13%, 0.13. Okay, that's what was shown to be true just last month. Okay, now what are we trying to investigate here? Well, up here, let's see, at a 5% significance level, can we conclude that the population approval rating has decreased? So that's the key word we're looking for here, decreased. So we want to know, is P actually less than 0.13? Okay? So we have the null hypothesis and the alternative hypothesis. That was step one. Okay? Now, what was step two? Okay? Well, it depends on if you're going by the book or the notes I gave you. Step two, according to the book, was determine which distribution to use. But with these particular types of hypothesis testing, with the proportions, we're always going to ensure there's a large sample size. So we're always going to use the Z distribution. So that was kind of a really simple step two that we leave off most of the time, especially with the proportions, because we're going to always use the Z, the standard normal distribution, when we're talking about proportions. So I'm going to go and skip over to the next step. I'll call it 2 in this point, and that is to draw the null model, essentially. Okay, that is to locate your critical values. I usually just call it draw the null model. Okay, which just means we need to locate our critical values and just see what would a distribution look like if the null hypothesis was true. Okay, so let's see here. If the null hypothesis was true, let's get a normal curve over here. Okay, if the null hypothesis was true, well, what would be true? That would be that the mean right here in the middle, okay, that's a Z value of 0, but P value equals 0.13. okay, which of course is a z value of 0. Okay. Now, we want to, okay, now I'll just put that there, equals 0, okay. We want to figure out what our critical values are. Now, our critical values are related to our significance level. Here we have a 5% significance level. Okay, now I guess we need to determine what type of test we're doing. And that is a function of our alternative hypothesis. We're concerned if the population approval rating has decreased. So that would mean if we're looking to see if P is less than what was previously known to be. That means we're going to be using a left-hand tail test. So a one-tail left-hand test. So our rejection region is going to be the left tail. So we want to find that critical value right there. So I'll label that Z crit equals, and we'll have to find that. Okay. Now, what is that shaded area under the curve going to be equal to? Well, that's alpha. Alpha is a 5% significance level. So that right there is alpha equals 0.05. Okay. Okay. Here, if it's a two-tail test, you have to split alpha in two and put half of alpha in each tail. But here we just have a left-hand, a one-tail test, so we put all of alpha in the left-hand tail. Okay. So now, how do you find the critical value that marks? And again, the shaded part, that is our rejection region. Is this area here, and this is non-rejection region. Okay. All right. So how do we figure out that z value? Now, again, we've done this a whole bunch. We just first started this in chapter 6. The way you find this critical value is to find z such that the area to the left of z is equal to alpha. Okay. So alpha is 0.05. So we want to find z such that z is to the left, such that the area to the left of z is 0.05. Well, the easiest way, if you have a TI or you know how to use a different kind of calculator, is to use the inverse norm function under the distribution menu. So the inverse norm of 0.05 you get is negative 1.64. So that critical value is negative 1.64. Oh, let's see here. 1.64. Okay. So if the observed z value that we find, in the next step, if that observed z value falls over here in the shaded region, which means that the observed z value will be less than the critical z value, then we reject the null hypothesis. If it lands over here, if that observed value that we're about to compute, if it lives over here somewhere in the non-reject region, then we would fail to reject the null hypothesis. So there is our null model. Okay. Again, this is kind of like what's going on if we assume the null hypothesis to be true. Okay. In step 3, we usually did stuff like write down the criteria for rejection. So that's what we just talked about. So I'll write those down real fast. If z observed is less than z critical, we reject the null. Okay. Another way, that's the critical value approach. Another way to reach the same conclusion, and this is always the case if I could draw an F all of a sudden, if P is less than alpha, we reject the null. Okay? Now, again, I can't stress this enough. We're only ever testing the null hypothesis. We are accepting well, I guess the better word would be use failing to reject the null hypothesis or rejecting the null hypothesis. If we happen to reject the null hypothesis, we by default just go with the alternative, assume that the alternative hypothesis explains our sampled data better than the null hypothesis. If we fail to reject the null hypothesis, that means that it appears that our sampled data are adequately explained by the null hypothesis. So that's kind of our criteria for rejecting the null or not. These are both the same thing. Okay, they're the same, two sides of the same coin. Both of those criteria. Okay. Now, step 3, that is to calculate our test statistic. That is, calculate Z, I like to call it Z sub observed. Okay, now this is the same way we calculated a Z-score in regard to a population in previous chapters. So that was p hat minus p over the standard deviation of the proportion sampling distribution. Now, we have p hat, we have p, we haven't calculated that yet. So actually, let's go back over here and calculate the standard deviation of this sampling distribution. So, sigma, oh, you know what? I said sigma sub p hat. Let me change that. Let me see here. Well, yeah, that's fine. That's fine. We'll work with that notation. Sigma sub p hat. Okay. Now here, the reason I was going to change that, I'm not sure if I'm right or wrong on this, but well, I know I'm right with the calculation I'm about to do, but as far as this notation goes, because we are assuming here that the null hypothesis is true. So when we're assuming the null hypothesis is true, we want to use P and Q. We're not talking about P hat and Q hat in our standard deviation. So that notation there is a little misleading, because we want to take here, our formula is the square root of P times Q, which is 0.13 times 0.87 divided by n, which is 1,000. Okay, so again, we're not using p hat, and we haven't even listed q hat, but q hat would be 1 minus p hat, but we use p and q here. So just be careful of that. Don't accidentally use p hat and q hat, because again, we're assuming the null hypothesis is true. So that's why we're using p and q, because p and q, those pertain to the null hypothesis. Okay, so let's calculate this. Actually, I need to do my calculator, so let's see. So 0.13 times 0.87 divided by 1,000. Then take the square root of that small number, and let's see here. We get 0.01063 8484. Oh, I'll just leave it like that, a bunch of decimals for the time being, because sometimes you can get into trouble if you round this standard deviation. If you round that too early, it really affects the answer later on. So let's just leave it like that. It's better to be safe than sorry, and we can round. We're going to round z here to 2 decimal places, so we can use this long answer here for the standard deviation, and then once we get to our z observed value, we'll round that one. Okay, so let's plug in here. Okay, so p hat is 0.111, so 0.111. P is 0.13, and the standard deviation of the sampling distribution is 0.01063 0.8484. Now, let's see what that equals. Okay, so I'm going to go over here and use my calculator for a sec. So 0.111 minus 0.13, then divide by that standard deviation. Oh, I messed up. Oh, sorry, I got to retype this. Sorry about that. So 0.111 minus 0.13 divided by the standard deviation. And if you round, again, this is a z-value, so we're going to round to 2 decimals. It's negative 1.79. Negative 1.79. That is z observed. Okay. Now, what we want to do now in step 4 over here is make our conclusion. Okay. Well, the way you make a conclusion is to compare. I like to graph z observed and see where it falls on the null model over here. Well, I didn't label this. Let me label this. The null model. Okay, so let's see here. Okay, well, I'll change colors here. Where does negative 1.79 fall? Well, our critical value that separates the rejection region from the non-rejection region is negative 1.64. So negative 1.79 is more negative than negative 1.64. So our z observed value, falls about right there. So z observed equals negative 1.79. So you see that observed value falls to the left. So if you go back over here to our criteria for rejection, we see, let's go change back here. We see that since z observed is less than z critical, we reject the null. Okay? Now, that's using the critical value approach. Now, let's show you how to do the p-value approach. So, the p-value approach is when you find the probability of getting a z-value of your observed or more extreme. So what's the probability of getting a z-value of negative 1.79 or a more extreme value than 1.79? Well, that probability, and I'll shade it for you, is this. Everything to the left of our observed z-value. So what is this pink shaded area? Well, how do you figure that out? Using your chart in the back of your book, or you can, you could use your calculator. So I'm about to use my calculator right here. What you can do is, okay, this is a standard normal distribution. So what you're going to do is go to the distribution menu. If you have a TI, and we want to use the normal cumulative distribution, and let's see here. Let's go from just a really big negative number, like negative 999. Oh, that's way overkill, to negative 1.79, and see what that probability is. Okay, so P, again, this is the pink shaded area. P equals, we're going to round to 4 is fine. Oh, let's give it some room here. P equals 0.00367. Again, what is that? That's the probability of having a z observed of negative 1.79 or less. That is a more extreme value than negative 1.79. So it's the probability of
of getting this value or a more extreme value if the null hypothesis is true. So P is 0.0367. Well, what do you notice about P? P is 0.367 and alpha is 5%, so 0.5. So we can also say that since P, which equals 0.0367, is less than alpha, which is 0.05, we reject the null. So two different ways to reach the same conclusion. You can use the p-value approach or the critical value approach. Most people find that when you're doing hypothesis testing by hand, the critical value approach is easier. We tend to use the p-value approach when we have software to help us, because it's much easier for the software to calculate automatically. We tend to use the critical values, again, when we're doing this by hand. Okay, so the conclusion to the first question is we reject the null hypothesis. Okay? So at a 5% significance level, can we conclude that the true population approval rating of the United States Congress has decreased over the past month? And we say yes, because we have to reject the null hypothesis. Remember, the null hypothesis is that the approval rating is 13%. We reject that and accept, and by default, accept the alternative, which is the population proportion has indeed decreased over the past month. So the population proportion is less than 0.13. Okay? We say that the null hypothesis does not adequately explain the sample data, the sample statistic that we gathered. Okay? Because the sample statistic we found, the p-value we found, is 0.0367, which means that if the null hypothesis were true, the result that we found would only happen 3.67% of the time, which certainly happens, but it's not super likely. So we conclude that that the population proportion has probably decreased to some extent. Maybe not as low as we found it to be, but it has decreased, which would help explain our sample statistic. Now, what happens if we, like the last sentence asks us to do, and increase the level of significance to 1%? Now that looks funny, increase. Increase is because we're creating a more strict criterion. Okay, we're being harder on ourselves as far as the criteria for rejecting or failing to reject the null. Okay, so what happens if we increase the level of significance to 1%? Now, where does the 1% significance, where does that even come into play? That only comes into play when we are drawing our null model as far as the rejection region is concerned. Okay, so let's draw another null model, assuming everything else is the same, except assuming we have a 1% significance level. So go down here. Oh, a little bit longer. Okay, draw. Oh, that's terrible. Okay. Now again, we're dealing with the left-hand test. That's going to be the same, but the only difference is where our shaded region is going to be. Because here, alpha is equal to 1%, so 0.01. That's that shaded region. Okay, again, the shaded region, that is our rejection region. Okay. Now, if alpha is 0.01, we want to know what is the z critical value, or the z value, such that to the left of z, there's only 1% of the area under the curve, or 1%, 0.01 area under the curve. So we take the, you use the chart in the back of your book, or maybe you remember this. I never remember these numbers, even though I use them all the time. And it looks like that z critical value, either using your calculator or the z table, is negative 2.32. So when we increase the level of significance, that changes our z value. Now this is still the null model. P, there would be, the mean would be 0, which would correspond to P equals 0.13, right there in the middle. This over here was certainly your non-reject region. And what we want to do now is plot that observed value again. Okay? So our observed value, remember that doesn't change. The observed value, nowhere in this formula here did we use alpha anywhere. There's P hat, there's P, and there's the standard deviation. So our z observed is still the same. Okay, so again we have a new null model that's based on alpha at 1% instead of the original 5%. And we want to see if our conclusion stays the same. Because if we're essentially raising the bar when we change the significance level to a smaller number. You're increasing the level of significance. So you're raising the bar. You're decreasing your type 1 error is the whole point of that. Okay? So let's see what happens if we plot our z observed value. So let's see here. Let's go back to that pink color and maybe scroll down slightly. So our observed value is negative 1.79. So you see that's a critical value, that value that separates the rejection region from the non-rejection region. That is a negative 2.32 z value. But what do you notice about our observed value? Our observed value is negative 1.79, which is over here to the right. Z observed equals negative 1.79. Okay? Where does that fall? It falls in the non-rejection region. Okay? So for part 2, when we increase the level of significance, that is, we raise the bar, we decrease type 1 error, the conclusion doesn't hold up. We fail to reject the null hypothesis, since in this case z observed is greater than z critical. Okay? Because our observed value fell in our non-rejection region. Now, be careful about when you write these inequalities, because these inequalities, you have to interpret what's going on, whether it's a left-hand tail, right-hand tail, or two-tail test. For instance, if we were talking about a right-hand test, we would always want in order to reject the null, we want observed value to be greater than the critical value. So you just have to be careful. That's why I always advocate drawing a picture and shading so you can tell what the criteria for rejection versus non-rejection are. Okay. Now, what about the alpha approach? Now, the alpha approach would be to calculate the area to the left of your critical, to the left of your observed value. So we want to know what is the area under the curve to the left of our z observed value. So this area here, what's that area? That's P. Okay? So that is P, again, is the pink shaded part. Okay? Now, what is P? How do you find P? Well, let's give ourselves some room. That is simply using the chart in the back of your book or using your calculator to find the area to the left of Z when Z is, again, negative 1.79. So I'm going to use my calculator really fast using the normal cumulative distribution. Oh, let's see here. Oh, you know what? We already done that. Where's my head? P is still the same. 0.0367. Of course. The area to the left of negative 1.79 doesn't change. The only thing that changed between these two null models was our rejection region. So P is still the same, but what do you notice here? P, so we fail to reject the null. Since P, which is 0.0367, let me fix that, 0.367, that's equal to P, which is greater, greater than alpha, which in this case was 0.01. The nice thing about the alpha approach, or excuse me, the p-value approach, is that you don't have to worry about these inequalities with your critical values. That's the one time I have students get mixed up, is when they don't draw a good picture, they don't draw a good null model, and then they always want to go by this criteria. If Z observed is less than Z critical, then you reject the null. That's not always the case. That statement right there is dependent on whether or not it's a left tail test or a right tail test, or perhaps if it's a two-tail, you have to do interpretation here. But in all cases, if P is greater than alpha, we fail to reject. And if P is less than alpha, we reject the null. That stays the same. So that criteria always stays the same, whether or not it's a one-tail, two-tail, left-right test. So that's one good thing about doing a p-value approach. The one pro that I find when you compare it to a critical value approach. Critical value, it's easier as long as you draw a good picture, but it can confuse you if you don't draw a good picture. Okay. All right, so let's just review. Let's go back up here to the top. We were talking about a sample proportion, using sample data to figure out if the population proportion had changed, specifically had it gone down. What we found is if we had a 5% significance level, we found that we would reject the null hypothesis and conclude that the true population approval rating of Congress had actually decreased over the past month. But if we were more strict with ourselves and had an increased level of significance, that is, we reduced the type 1 error, we reduced alpha, then you find down here that we could not reach that same conclusion, that we failed to reject the null hypothesis when we raised the bar on ourselves. So again, alpha is one of those things. Alpha levels are set by discipline. You know, if you're doing medical research, you want to most likely have a higher alpha than if you're doing market research, trying to figure out what type of sodas people like the best, or something like that. Because obviously nobody's life depends, on if you like Coke versus Pepsi or something like that. So different disciplines will set alpha levels differently. So it's not one of those things that, like we just did right here, that you would just kind of, on a whim decide to change the alpha level. That's where people get into trouble, if the results aren't working out and they kind of change alpha on the fly. That's where you get into trouble. So, but for the purposes of illustration, I wanted to show you how a conclusion will change based on alpha. Okay, you can be more relaxed and allow a 5% alpha, or you can be more strict and increase and have a 1% alpha, and that changes the conclusion of whether you reject or fail to reject the null hypothesis. Okay, so I think we've talked about this example enough. Of course, if you ever have any questions, you can always shoot me an email, or you can ask a question underneath on this video, and I'll try to respond there. Or of course, you can always swing by my office. Hope this has been helpful. You guys have a nice day. I'll see you soon.